Hello, my name is Paula. I'm a researcher at PUC-Rio, and now I present the compositional pore-network modeling of gas flooding in gas-condensate reservoirs, which I conducted with Professor Márcio Carvalho. So to introduce our study, it was motivated by the fact that in gas-condensate reservoirs, the production can be significantly reduced due to condensate banking. To explain this, I'll use this figure here of producing well in a reservoir. And what happens normally is that we form this ring of liquid around the producing well, which hinders a lot the gas reduction. And this happens because if this line here represents the reservoir pressure, and this line here represents the dew point of the reservoir fluid, what we have is that far from the well, we have a single phase region with only gas, and close to the well bore, we shift to a two-phase region and condensate dropout takes place. And if we analyze this at a pore scale, we can see that before condensate banking, the gas has many paths to flow, so the production can be relatively high. However, after condensate banking, we form those films of liquid around the grains and also those bridges. And as a result, previous gas flowing paths are blocked by liquid, and that reduces a lot of the production. So when this happens, a possible remediation is to inject gas in the reservoir and to remove this accumulated liquid. But the problem is that for immiscible two-phase systems, we have a low microscope efficiency. So if we try to inject gas to move the liquid, the gas probably would find those preferential paths to flow, and most of the liquid would remain in the porous medium. So in this case, what we wanted to achieve is the injection of a gas that also promotes the condensate revaporization, so that we can have a more efficient gas flow reestablishment. Therefore, our goal was to evaluate gas injection scenarios for condensate banking removal at a pore scale with a compositional pore-network model. So moving to methodology, what we did was basically to reproduce gas flooding following condensate banking using a compositional pore-network model for gas condensate flow. And some of the highlights of this model are, first, the geometry. We formed the porous medium with convergent, divergent, circular pore elements. In those pore elements, we devised some transport rules specifically to represent condensate dropout and the coupled flow of gas and condensate in porous medium. And finally, the compositional formulation was based on the work of Collins and others in 1992. And in this formulation, we've implemented a flash calculation using the Penguin-Robinson equation of state. So using that model, this is the gas injection procedure that we've implemented. First, we represented the porous medium as this sandstone-based network with a permeability of 169 millidensity and the porosity of 17.1%. And in this network, we performed two different steps. The first one to accumulate condensate, and the second one to try to mobilize this condensate with gas injection. So detailing those steps, in the first, we inject 25 pore volumes of this mixture here, representing the reservoir fluid with 8 different components, which gives us this phase diagram, and this step was performed at the temperature of 60 degrees Celsius at those 6 different pressures here, so that we could evaluate the effect of pressure in this method. Then, after the condensate had accumulated, we moved to step number 2, which involved the injection of also 25 pore volumes of one of those gases here that could be either carbon dioxide, nitrogen, methane, ethane, or produced gas. And in this step, we always injected gas at the same flowing velocity of 35 meters per day. So after we did this, now we can analyze the results. So the first results I'll show, they focus on the effect of pressure on condensate recovery. So here we have those 3 graphs in which we can see the condensate saturation as a function of the injected pore volumes in the network. So in each of those 3, at the first 25 pore volumes, we have the injection of that reservoir fluid, so the condensate saturation increases and we are forming the condensate bank. Then at the last 25 pore volumes, we have the injection of those tested gases, and we try to mobilize this condensate. This graph here in the left was obtained at the highest tested pressure of 22 megapascal. This one in the middle at an intermediate pressure of 19.5, and the one on the right with the lowest tested pressure of 14.75 megapascal. So first, focusing on the high pressures, the first thing we can see is that we have a relatively low liquid saturation. So after the injection of the reservoir fluid, we have only around 15% of liquid. And this happens because we're really close to the dew point pressure and the liquid dropout is low. Then the second thing we can see is that CO2 in the curve in pink and C2, the curve in orange, they remove all the accumulated condensate. And that happens super fast. So we can see that in the first 5-4 volumes of injection, we already have close to zero liquid in the network. The second best gas was methane. It left only 1.1% of liquid after the 25 injected pore volumes. And also we can see that nitrogen and produced gas had similar performances, leaving around 3%, 4% of liquid, but nitrogen had a higher rate of liquid removal here in the beginning. Now moving to intermediate pressures, we can see that unlike the previous case, we have a high liquid saturation after the reservoir fluid injection. We have around 36% of liquid. And in this case, the gases showed very different performances. Again, CO2 and C2, they show superior ability to recover condensate when compared to the other tested gases. C1 and C2, they have similar performances, but in the end, they still left around 15% of liquid in the network, and the produced gas could recover slightly less liquid than C1 and N2. And then finally, moving to the lowest tested pressure, we again have a high liquid saturation. And in this case, unlike the previous ones, all injected gases perform similarly. And after the 25 pore volumes of gas injection, most of the condensate remains trapped in the porous medium. So we can see that the pressure has a very important effect on the recovery of condensate. At high and intermediate pressures, we could recover most of the condensate depending on the injected gas, but at low pressures, none of the gases could mobilize the liquid. And to illustrate it better, here we have the representation of the networks at all the 6 tested pressures after a CO2 injection. These colors show the CO2 content in the network, so the yellow paths have very high CO2 content and the purple paths have very low CO2 content. So we can see that from 22 megapascal down to 19.5 megapascal, there's a progressive reduction in the volume swept by CO2. At 17.75 megapascal, there's a significant reduction in the volumetric sweep efficiency during CO2 injection. And at the lowest tested pressure, most of the volume is bypassed by the CO2 injection. And the other thing we looked into in the results was the recovery of heavy components, because ideally not only we want to evaporize the light components in the liquid, but also the intermediate and heavy components. So in those graphs here, we have the recovering moles as a function of the pressure and the injected gas for the C10, the decane, and the C16 hexadecane in the network. So we can see that first, analyzing together the CO2 and the C2, we can see that they can recover the highest amounts of C10 and C16 for all tested pressures. And also we can see that the recovery is significantly reduced when the pressure becomes lower than 19.5 megapascal. Then analyzing the recovery obtained with methane, we can see the same trend observed with the CO2 or the C2, but the absolute recoveries are lower. Then we can see that the recovery with the N2 injection follows this same trend only for the decane case. And for the hexadecane case, the recovery for all tested pressures is very low and almost constant. And this indicates that when the N2, the nitrogen, is injected in the network, while it can revaporize the decane, it's not enough to revaporize the C16, so it remains trapped. Most of it remains trapped in the porous medium after the injection. And finally, we could see that the injection of reduced gas also displayed a different behavior with maximum recoveries at intermediate pressures. So after conducting this study, our conclusions were that a procedure to evaluate condensate recovery with gas injection at the pore scale was successfully implemented, that gas injection can be an effective method to eliminate condensate banking, that the injection of C2, ethane, and carbon dioxide display the overall most favorable results, and the DER method was significantly more effective at high pressures. As future work, I think that it would be important to evaluate the effect of gas injection rate on the condensate recovery, and also evaluate the effect of porous medium heterogeneity on the recovery of condensate. And finally, I would like to thank all the agencies that funded this work. Thank you.